refraction notes, and we're going to start off talking about the photoelectric effect. Now, some of you saw the little demonstration with the light bulb in it and the moving propeller. Actually, it's the photoelectric effect that actually makes that work, because as soon as the light hits the little propeller, the electrons eject off the metal. So with the photoelectric effect, you're going to have an ejection of electrons from the metal, but only certain frequencies make it do that. That's why it worked with the overhead projector, but it doesn't work when you hold it up to fluorescent lights. So we're going to have a brand new formula for the energy of a photon we can get from that, called E equals HF. Now, you got to know what H is. H is a brand new constant. We're going to call it Planck's constant, named after a famous scientist. And it's 6.63 times 10 to the negative 34. Now, it's supposed to be 6.66. That's satanic. So we just lowered it a little bit by 3. And that's why we lowered it by 3. And that's why you got the negative 3. And we just put the 4 behind it, which adds up to 7, which is our lucky number. Woo! So therefore, Planck's constant is going to be 6.63 times 10 to the negative 34 joules seconds. Next question says, well, what's the energy then of a photon with a wavelength of 1 times 10 to the negative 10? Well, we're going to use that formula there of E equals HF, but unfortunately, they didn't give us F. So let's go back to that last chapter where we talked about the fact that velocity equals F lambda. Well, if I need F, that simply means that velocity over lambda equals F, so I'm going to plug that in for F here. So I'm going to have H times velocity divided by lambda. So let's plug all this stuff in now. I got 6.63 times 10 to the negative 34 joule seconds. Multiply that by the speed of light, which is 3 times 10 to the 8th. Please make sure you know that. That's going to be meters per second since it's speed. Divide that whole slack mammy by the 1 times 10 to the negative 10th meters. So these meters cancel out here, these seconds cancel out there, and you're left with joules, and the number is a real small number of 1.989 times 10 to the negative 15th joules. So even though it's an X-ray, we still have a small amount of energy there. The next one you have to do is figure out the amount of energy a yellow-green photon. Well, this is going to have less energy because it's now visible light instead of an X-ray. So we'll do the same formula again, E equals HF, but instead of F, I'm going to put in a velocity and a lambda. Just go ahead and put in all the numbers now. We got 6.63 times 10 to the negative 34 for Planck's constant. That's joule seconds. You got a velocity, once again, of 3 times 10 to the 8th, because it's moving at the speed of light, meters per second. Divide that whole thing. Now you got a wavelength of 533, but it says nanometers. We got to go back to that second week of school where we learned that nano means negative 9. So I'm going to do 533 times 10 to the negative 9th meters. Put all that together now, and you end up getting 3.73 times 10 to the negative 19th meters. The next one says the law of reflection is a definition and a formula. And in class, we got talking about how if you shine something on a mirror, so for instance, this is a flat surface, I got your little mirror down here. Anytime I put these little dash marks, it means it's a mirror. Well, if a laser would be coming in here at, let's just say it comes in at a 60-degree angle. Now, what I mean by a 60-degree angle, and that's what the normal, so the normal would be a perpendicular line with the surface, so that green line there. Well, if it comes in at a 60-degree angle, what the law of reflection says is it has to go out at a 60-degree angle. So the angle of incidence, that's the definition here. So the angle of incidence. Now, what we call the angle of incidence is the angle that the laser comes in at. So coming in at this 60-degree angle here equals the angle of reflection. And so that would be the angle on the right-hand side over here. So the way I'm going to write that is theta I, so here's theta, which means the angle, I means of incidence, equals the angle, which is theta again, of R of reflection. This next one, you have a mirror that's, two mirrors here that are 120 degrees apart, but you have this laser now coming in at 65 degrees with the normal. Okay, so let's say this is a 65-degree angle right here. But don't forget that the laser is going to bounce depart from the normal at 65, so it's also going to come like this. It's going to come back and hit this mirror over here, and that's not a really straight line. You have to general this, so that's 65. Well, if that's 65, that means that this part here must be 25, if we can read all that. And don't forget that all the angles of a triangle have to add up to 180. And so therefore, 120 plus 25 gives you 145. So that means this angle over here must be 35. And when it bounces off the normal, here's another normal with this mirror. Remember, a normal is at a right angle with the mirror. That means that this angle must be 55. And so that means it bounces off at a 55-degree angle with the normal over here. All right. Next one says define refraction. Refraction is going to be that bending of the waves when the light goes through a barrier. I don't know if you remember the demonstration where we looked at a pencil that was stuck in a glass of water and it looked like the pencil was broke. So whenever light travels across a boundary between two media, what I mean by two media, let's say that one substance the light goes through is air and another one is water. Those are two different media. So therefore the light's going to travel slower in one than it does the other, and it bends a little bit. That bending is what we call refraction. So when light moves from a material with a high speed, like air, to a material which the speed is lower, the angle of refraction is less. You got to remember, it's bending towards the normal, and the angle of incidence, so it bends toward the normal. I'll give you an example of that real quick. Let's say I got my surface right here. I'm going to have this part down here is the water. This is water. This part up here is going to be air. When the light would come in, let's just say it's coming in here, like so. My normal is going to be this green line going up and down. That line is going to bend towards normal. So let's just say it came in at a 45-degree angle. When it bends down, it might come in at or go out at a 40-degree angle. So it's actually bending down towards the normal. That's what that means. So if you go where light moves from a material with a lower speed of light, like water, to higher, the angle of refraction is greater, so it should be greater here, than the angle of incidence, so the light bends away from the normal. This is going to be really, really important when we get into diamonds and things like that, too. So when we calculate the index of refraction, that's what's going to help us figure out how much the light's going to bend. It is symbolized by an N. And here's how easy it is to figure it out. It's different for every substance. So you can figure out the index of refraction for something and tell what substance it is. We're going to take the speed of light in a vacuum and divide that by the speed of light in the medium. So that'd be like the speed of light and air and water or whatever. So let's just put that down as C, which is the speed of light. B is going to be the speed of light in the actual medium. And on the next video, it tells you how to do the second page, and we're actually going to be using that formula the whole time. We'll see you in a bit.